Hi, this is Biostatistics, Prediction and Association, Part 2, Modeling Relationships, and your instructor is Dr. Marge Benham-Hutchins. The objectives of this presentation are to explore simple and multiple linear regression, evaluate the assumptions for regression analysis, make inferences based on regression analysis results, and then learn how to correctly report regression findings. Regression is used to make predictions, specifically to predict values for an outcome variable, which is your dependent variable, and to predict an outcome from one or more predictor independent variables. So we will begin with simple linear regression, and this is where we will look to predict the value of the outcome variable from a single predictor variable. As I mentioned, simple linear regression is when you have one predictor variable and one outcome variable. It's based on a linear relationship between the predictor variable, the independent, and the outcome variable, the dependent. The higher the correlation, the better the prediction. It is important to be familiar with the simple linear regression equation because you will be using this later when you're reporting your results. So it's the y prime, which is the predicted score, equals the intercept, the point where the regression line crosses the y-axis, plus the regression coefficient, the rate of change in y given a unit change in x. Since simple linear regression is an inferential statistic, you will also be using a model that includes your hypotheses. So you will hypothesize that the model is a good and significant prediction model, and then your null hypothesis is this model is not a good prediction model. And a model is said to be a good model if the result is significant and not a good model if the result is not significant. This is another thing that will come up later when you're discussing your results. It is also important later when you're discussing your results that you are aware of the simple linear regression parameters. Your hypothesis is that the independent variable is useful for prediction, and your null hypothesis is the independent variable is not useful for prediction. So a parameter is said to be a good predictor if the result is significant and not a good predictor if the result is not significant. Simple linear regression begins with examining the relationship between the variables through the use of a scatter plot. You can also verify what you saw in the scatter plot with a correlation coefficient. If the correlation coefficient is not significant, the analysis stops and the non-significant correlation coefficient is reported. If a correlation coefficient is significant, then you proceed to the regression analysis. I will provide a simple linear regression example. Our research question is, does severity of injury predict recovery after severe brain injury? The predictor variable is severity of injury, and the outcome variable is recovery after severe brain injury. One of the first things you want to do when you're doing a regression, just like other inferential statistics, you want to start with doing descriptive statistics on your variables. This will also give you the sample size and give you some information on the particular variables that you have selected. The next thing you want to do is run a correlation. You need to remember that if the correlation coefficient is not significant, the analysis stops and the non-significant coefficient is reported. If it is significant, then you proceed to the regression analysis. And you can see on this output that the correlation coefficient is significant. You will have an opportunity to actually complete a regression analysis when you do the exercises in the Cronk book. One of the things you're going to have to decide, and that is about variables to enter or remove. And in this particular case, this is the output showing that Model 1, we entered severity of injury. We didn't remove any variables, and the method we used was enter. In other words, we selected it. And it indicates that all requested variables were entered, and the dependent variable is recovery after severe brain injury. Another component of the regression analysis output is the model summary. And here you want to be able to look closely at the R squared. And this is called the coefficient of determination, and it gives you the proportion of the variance of your dependent variable that can be explained by variation in the independent variable. For example, 17% of the variation in the dependent variable, recovery after severe head injury, can be explained by variation in the independent variable, severity of injury. Another component of the regression output is the ANOVA. We'll go into more details on ANOVAs in our next chapter. But on this particular table, there are a couple things to pay attention to. And one is the degrees of freedom, which we've discussed is the number of values that are free to vary when computing a statistic. So for this example, we only have one predictor variable, and that is severity of injury. This table also gives you the F statistic, which is the mean regression sum of squares divided by the mean error sum of squares. So this is an important part of your regression reporting. The value will range from 0 to could be a very large number, and the value of F is the probability that the null hypothesis for the full model is true. And you can also see your significance level here. It's significant at less than 0.001. So for this particular model, you also have some output information. The predictors, the constant is severity of injury, and the dependent variable is recovery after severe brain injury. So when you see this output, you need to examine this chart and look for these particular components. So this is another output table you will get when you run your regression, and it is the coefficients. And here you'll note that under B, you will see the constant, which is the dependent variable, recovery after severe brain injury. And that number, it's 38.187. So that's important to know. You have A as part of your equation. And then B is severity of injury, and that is the 3.132. And when you are reporting a result, you're going to insert these values into your regression equation. So based on this simple linear regression model, our conclusion is that the severity of injury was a significant predictor of recovery after severe brain injury, and severity of injuries explains 17% of the variance in recovery after severe brain injury. And then the last part is how you would write out your regression equation for your report. And so that would be recovery after severe brain injuries equals 38.19 plus 3.13 times the severity of injury. As we discussed earlier in class, phrasing results is very important. In a simple linear regression, you want to make sure you include the direction, the strength, the value, the degrees of freedom, and significance level of the regression. In addition, you want to make a statement of the equation itself and include that. So here's an example from the example that I just provided. A simple linear regression was calculated to predict if recovery after severe brain injury was based on the severity of injury. A significant regression equation was found, and then you put your equation in there, and you make sure that you include your p-value, your F statistic, your degrees of freedom, with an R squared of 0.171, which is what you're going to use to describe the variation in the recovery. The predicted recovery after severe brain injury is equal to, and that's where you plug in your equation, 17% of the variation in recovery after severe head injury can be explained by variation in the severity of injury. Now, not only should you use this type of wording or something very, very similar when you're reporting your results, but this is something you should look for in the various papers you're analyzing and evaluating for your evidence-based practice. So if it is not significant, you want to still include the ANOVA and the R-squared results, but not the regression equation. And here's an example. So now we're going to talk about multiple linear regression. Basically, this is the same as simple linear regression, except that you're going to predict the value of the outcome variable using a combination of predictor variables. Multiple linear regression is an extension of simple linear regression, and you will use two or more independent variables that are jointly used to predict a single dependent variable. And here's an illustration of the multiple linear regression equation. Note that for your predictor variables, you will only have partial regression coefficients because of the contribution by the other independent variables in the model. So this is the regression equation for multiple regression, and it is just providing all the terms and the details I provided in the simple linear regression content. So the goal of multiple linear regression is to find the best linear combination of independent variables that jointly predict an independent variable. The level of measurement for multiple linear regression, the outcome variable can be a continuous variable, which is, if you recall, that's an infinite number of possible values between two observed values. And predictor variables can be categorical or continuous. Categorical is when numbers are collected in groups or categories. Just like other statistical analysis, there are assumptions that are important for valid results with a multiple linear regression model. The first would be linearity. That is that the relationship between the dependent and independent variables should be linear. You could check this with a scatter plot. Independent. The subjects are responding independently. And when you're running your linear regression in SPSS, you can select and check the box for Durbin-Watson statistic, and it will then run that for you and let you know whether or not you have independence. Normality. This is where you have normal distribution. This can be investigated with a histogram or statistics tests such as those listed here. An equal variance, this is also important, and this could be checked with a residual plot. And this is another option that you could check in the SPSS window when you're running the analysis. So multiple linear regression has another assumption, and that is that there will be no or little multicollinearity. This can occur when there is a high correlation between two or more of your predictor variables. And this can cause one predictor variable to be used to predict the other. This can create redundant information, skew your results, and develop a questionable output in your regression model. So a couple examples of this might be a person's height and weight, age and the sales price of a car. The age of the car and the sales price of the car might be very highly correlated. There's some more information on this with this particular link, and also your textbook has a little bit more on it. When you're doing a multiple linear regression, you have a variety of models you could select from. There are enter, hierarchical, stepwise, and you could do stepwise forward or backward. To determine which one to use, it depends on where you are and what stage you are in your analysis. So for example, enter, you may use this only as a rough examination of the variables. This is where you could put a variable in and take it out and just examine the various components of your data. Hierarchical, you would use it only when you have substantial knowledge about the variables, such as what to control for and what to test for. Stepwise, here you're going to use this when you want to explore the data without preconceived ideas and determine the best prediction model. So multiple regression is very similar to other type of statistical analyses that you'll do with SPSS, and that is that you're going to get multiple output tables and information. So with multiple regression, you'll get the descriptive statistics, which is where you'll be able to look closer at your variables, at your N, and correlations to see are there already correlations between the various variables. You'll have an output that'll show you what variables are entered and removed. There'll be a model summary and then another model summary with change statistics, the ANOVA, and then the coefficients under standardized and standardized. This example comes from the Cronk workbook, and I thought it was a good way to show multiple regression reporting. So in this particular case, you're going to look at your model summary. And if you notice, I have the circles around the different components to draw attention and then colored text to the side to indicate where that goes in your reporting. So here you have a multiple linear regression was calculated to predict participants' weight based on their height and sex. A significant regression equation was found, and if you see all those in purple are there in the ANOVA table, with an R squared of 0.993, that's in your model summary. And then you have your regression equation here, and that's where you pull out from the coefficients that are the under standardized coefficients, the B. This presentation gave an overview of simple linear and multiple linear regression. It's just an overview to help you become familiar with these particular statistical tests, these inferential statistical tests, and to help you in writing up results and interpreting the literature. If you are going to do any type of regression analysis with your project, I recommend that you consult with a statistician who will help you with some of the various assumptions, setting up your model, and work with you so that you will get valid results. Here's a list of some references. The Andy Field book, there's a newer edition than this, is an excellent book that one is very similar to the Cronk book, but goes into a lot more detail on running various statistical analyses. And then the resources below are on the multicollinearity, and then as you may have already figured out, there's actually a way in APA to report statistics. And so the Purdue OWL has some of that, but you also will find much more information in the APA book on how to actually report your statistics in a consistent manner.